this sort of layers of bits of the star that are fusing and bits that aren't. You're eventually going to get a core that can't fuse. It's made out of carbon and maybe some oxygen. You can get 4 heliums to fuse oxygen, so you'll be left with heavy stuff in the core, but that stuff's going to get dredged outwards as the outer layers are fusing, but they're fusing in spikes, they're fusing in pulses. And so these pulses, as the shells are burning, are going to push the outer layers and the dredged up stuff out. And so you're going to be left with various remnants that get pushed out. And these remnants, these are what are called planetary nebula. The reason they're called this is because when people saw them the first time, people thought that they were planet like. They didn't think they were stars, or they didn't think they were like stars. These are not where stars form. We talked about where stars form and where planets form in solar nebulas or in stellar nebulas. These are remnants. This is putting the matter back out into space, not taking it and making a star and a set of planets. I've put a link in here. I highly recommend lots of pretty pictures. These are all pretty things. Planetary nebula are kind of interesting. They have different ways of looking. The expansion is not uniform, and so you get different patterns. You can see that there's some sort of axis here, whereas this we're kind of looking at it from the pole down, and it's nice and symmetrical outwards. All right, and so again, there's some more. This is what's called the ring nebula, and it's nice and round, and there's a central sort of element in it, or a few central elements in the background, but there's a thing that it's expanding from, and then further in there's more material. And what's happening is the core is still producing lots of energy, and it's energetic photons, it's X-rays and such. And so it's ionizing this gas that's being pushed outwards. And so that's why you see these pretty pictures. It's pretty because you're exciting the hydrogen and the other elements in these nebula. This is the Cat's Eye Nebula. If you've ever played with marbles, there's what's called a cat's eye, which looks like this. If you've seen a cat, it doesn't look like a cat's eye. I don't know why. So there's again another view of the cat's eye, and then this is several different planetary nebulas from basically viewing from different angles. All right, and that's what's going on is because the star is not necessarily symmetric, the outer expansion is not symmetric. What you see depends on your perspective, how you're oriented relative to the expansion. So at this point, the material presses outwards. There's no way that the star is going to produce any newer stuff. Right? Basically, carbon and oxygen is the limit, and the core will contract, and that core will leave what's called a white dwarf. It'll be a remnant that's supported by degeneracy pressure. Right? And so this is the track that you see. It leaves the main sequence and expands. The initial helium fusion ignites, and it goes down this horizontal branch. And then when that runs out, you'll get double shell burning, and that'll be what pushes off the outer layers, and then the core will drift and then start to cool off and dim out. So imagine the sun. We're here. In about 5 billion years, maybe 7 billion years, it'll start to spike. And the initial spike doesn't take as long as the main sequence. This is, 100 million years or so until helium starts, and then it'll be stable, and then you'll get these thermal pulses from the double shell burning, and that will push off the outer layers. All right, so this is the luminosity that we expect. Basically, giants put out a lot of luminosity.